This is checkpoint 3 on gravitational fields, so now we're introducing the idea of gravitational potential. Here's our first question. So we've got two positions x and y on this planet, so it might be easier to realise what we've got here as a planet with a big mountain on it. Okay, so this is x up here, y is down here, and we're asked to talk about two things: the gravitational potential at x compared with y. Well, you've lifted it up from y to x, so x, it must be greater, so it's not d. The angular velocity at x compared with y, well, they're both going to go round in the same amount of time, so it doesn't matter if you're up the mountain or if you're right down here in the middle, you still take the same amount of time to get round, so the angular velocity is the same. Okay, so that gives us b. Okay, this question actually is on the other checkpoint as well, so if you can't do it now, you're in trouble. So the gravitational force on two spheres, each of twice the mass of the original sphere, and the separation is twice as much. So just to remind you, we've got two spheres, m and m, with the separation of r. We replace these with another two spheres with 2m and 2m with the separation of 2r. Okay, so on this one the force is gmm over r squared. On this one it's g times 2m over 2r all squared. The 2's all cancel out because this one's squared, so it gets you back to gmm over r squared. So it is in fact the same force. Okay, number 3, this is a crucial question to understand. So we've got here a graph of potential against distance. This really is like a hill. You can imagine if you were taking a picture of a hill, this is what the hill would actually look like. Obviously this is a very big hill because we're going a long way away from the Earth here. And the gradient of the hill is the gravitational field strength. So when you're close to the planet, this line is steep. This line is steep because you're making a big difference in potential for every small difference in height. When you're over here, the reason the gradient is smaller is because you're only making a small increase in potential for each increase in height. Okay, remember mathematically we can do this because to get the potential we're doing the integral of the field strength with respect to distance. So the other way of writing that is dv by dr is what g is. The gradient of the potential is the field strength. Okay, so the magnitude of the gravitational field strength at that point, a. Not the gravitational constant, that's g, that's got nothing to do with it. Not the mass of the Earth. And the potential energy at the point the gradient measured, well, that is the point, isn't it? That's not the gradient, that's the actual point here. Okay, here's the long answer, first long answer question. So we need the gravitational potential at a distance of 2r from the Earth. So we're just reading this off the graph. So depending on the accuracy of your line, this is about minus 31 megajoules per kilogram. Okay, don't miss the units here, megajoules. So the increase in potential energy of a 1200 kilogram satellite raised from the surface to 3r. Okay, so we've got to be careful here. They've asked us for this 2r and then they haven't asked us to use it down here. So we're going from the surface, which actually tells us down here is minus 62.5. So we're going from minus 62.5 megajoules per kilogram. Let's just put the units there just to be safe. To 3r. Okay, and here's 3r. So 3r goes across to about minus 21 megajoules per kilogram. So the difference, to be strictly correct, is where we're going to take away where we came from. So given the accuracy of reading this graph, that comes to about plus 41.5. It's going to take us energy to go from r to 3r. So something like 41 megajoules per kilogram. But remember, that's in megajoules per kilogram. So to find the energy, we have to do m delta v. So this is a 1200 kilogram satellite. The more mass your satellite's got, the harder it is to move it. 41.5 times 1200 is 49,800. So 49,800 megajoules. Okay, or if you like, 4.98 times 10 to the 10. So this is G equals minus delta V over delta R. Use the graph to find the gravitational field strength. So this is your clue as to how to do this. Okay, and if you go back to the earlier multiple choice question, the gradient, this is about finding the gradient of the graph, and we're at this point 2r. So the way to find the gradient at this point is to draw a tangent. So you need a nice big tangent. So I've gone up to 4r and down to 0. Okay, so if you do that, then you'll find that G equals the change in potential, which was 63 megajoules, divided by the distance, which was 4r. 4r is 4 lots of 6.4 times 10 to the 6. Okay, if you do that, then you'll get an answer of approximately 2.5 newtons per kilogram. Show that it's consistent with it being 10r. Well, we know how strong gravity is because gravity is proportional to 1 over r squared. So at a distance of 2r, right, the new g is a quarter of the old g, 1 over 2 squared. Okay, so we know it's 10. So 10 divided by 4 gives us our 2.5. Okay, so we could have worked that out without using the gradient, but that confirms it. Okay, communication satellites are in geosynchronous orbits. Okay, geosynchronous, geostationary, you can just treat those two terms like the same thing. So two features of geosynchronous orbits. Okay, one is it must take 24 hours. That's perhaps the obvious one, because if you don't take 24 hours to go around the Earth, you're not going to stay above the same point. But also it's above the equator. I do like to just explain this one. So here's the Earth. If this is the equator, okay, you might imagine that if you live in England, let's say, that you can put a satellite up here directly above, beaming its signal down to England, right? But what would happen is that would have to follow an orbit that went round like this, so it always stayed above the same point. If you do that, you've got to think of the direction of the force. Well, the direction of the force is towards the centre of the Earth, but what you want is a direction towards the centre of the circle, so that's not going to happen. It's going to get pulled down, right? So everything that was going around like this is eventually going to get pulled down into an orbit, so it's going around the equator. Okay, so given that the mass of the Earth is this and the mean radius is this, the radius of geosynchronous orbits must be this, so calculate the increase in potential energy of a mass of 750 kilograms raised from the surface of the Earth into geosynchronous orbit. So, okay, we know the formula for the potential, minus Gm over R. So the delta V here is the new one, which is minus G over 4.23 times 10 to the 7. Take away the initial one, Gm over 6.4 times 10 to the 6, because we're starting from the Earth. So delta V is minus 6.67 times 10 to the minus 11 times 6 times 10 to the 24 times 1 over 4.27 times 10 to the 7 minus 1 over 6.4 times 10 to the 6. And that will give you 5.3 times 10 to the 7 joules per kilogram. But we're moving a 750 kilogram satellite, so the energy we need is m delta V 750 times 5.3 times 10 to the 7, which gives us 4.0 times 10 to the 10 joules. Okay, gravitational potential, important that you learn this definition. So it's the energy required per unit mass. Okay, don't miss this bit out because it's going to be in joules per kilogram. So it's per unit mass or per kilogram to move a point mass from infinity to that point. It always seems like a very strange definition because, of course, it won't take any energy at all to move from infinity to that point. It's going to fall, but that's why we get a negative number. use the following data to calculate the gravitational potential at the surface of the moon. So we know what it is at the Earth. So for the Earth, V equals minus G ME over RE. Okay, no squared here. Okay, remember we're on potential now, not forces. So this is all for the Earth. For the moon, okay, obviously it's going to be the same. G M moon over R moon. So what we need to do is to find, put in the missing numbers here. So V moon equals minus G. Instead of putting the mass of the moon, I can put the mass of the Earth divided by 81. And then instead of putting the radius of the moon, I can put the radius of the Earth divided by 3.7. So if I rearrange that, that gives us V moon. So the 3.7 comes on the top. 3.7 minus G M E over 81. RE. Okay, but this bit here we know is this 63. So minus 3.7 over 81 times 63 times 10 to the 6. Okay, gives us an answer of 2.9 times 10 to the 6, or 2.9 megajoules per kilogram. Okay, and the last one, sketch a graph to indicate the gravitational potential. Okay, so let's just plot a few points. So we know at the Earth it's minus 63. We've just worked out that the moon is only minus 3, so it's only a 20th. So you don't need to plot this out, but it's only going to be fairly small down here somewhere. Okay, there's also a point that you might remember, 9/10 of the way it's a minimum, but it's not as low as 0, but it is higher. So you're going to come up from the Earth, follow a curve, not quite get to 0, and then go down again to the moon. So something like that for 3 marks.